Our world is full of new and exciting inventions that continue to push the boundaries of technology forward. Every day, it seems something new is announced, developed, and implemented that changes how humans interact. Just in the past few decades, cell phones, internet speed, medical breakthroughs, and the reinvention of basic infrastructure is beginning to change the norms in our everyday lives. But have you considered how these changes in science, engineering, and medicine occur? To most of us, on the outside of these revolutionary practices, it seems like magic when innovations appear in our lives overnight. In reality, it's years of painstaking work, trial and error, and rigorous testing that occurs before a finished product is ever realized. Researchers in the world of engineering and science move in small incremental steps, slowly building a case for these new revelations until they are sure technologies are ready to be shared with the world. In fact, there is an old saying in research, quote, "An amateur works on a task until they get it right, but a professional works on a task until they can't get it wrong," end quote. Fortunately for all of us, over the past few years, NASA, the FAA, and industry have been engineering the next big idea that may completely change how we interact in our world with the implementation of unmanned aircraft. The idea for inclusion of these aircraft is not new. The basic concept for small flying vehicles has been in popular culture and in the limelight for quite some time. But until recently, these vehicles have rapidly accelerated off the drawing board and into the skies. Over the past few years, NASA has been testing and validating research associated with unmanned aircraft through a project called Unmanned Aircraft System Integration in the National Airspace System, or UAS in the NAS project. This project spanned several years and addressed many of the early concerns of how unmanned aircraft would be integrated into our national airspace. After years of study, the UAS in the NAS project has tackled many of the early concerns. But one last big hurdle remains: to successfully demonstrate how unmanned aircraft will work in harmony within the national airspace. With this in mind, the final phase of testing, called the Systems Integration and Operationalization Demonstration Activity, or SIO, has begun in earnest. Throughout our country, at various NASA field centers and other testing locations, NASA has assembled a core strategic group of researchers to analyze and test unmanned aircraft through the SIO demonstration. Some of the key flight activities will include using various sized unmanned aircraft built by 3 different companies to highlight commercial UAS missions that have the potential to provide economic and public benefit to the American people. Throughout the testing, NASA plans to document best practices and lessons learned from the SIO activity and provide it to the UAS community to prepare us for routine commercial unmanned aircraft operations in our communities. On this episode of NASA X, we will take a look back at years of testing and development that have led up to the SIO demonstration flights, and we'll meet the companies that are helping to make these flights happen. This research and engineering has the potential to influence a massive shift in how we receive products and services, and may ultimately make an impact on how people travel and interact in our world. To understand why the NASA team has set up the SIO demonstrations, we first have to look at why integrating unmanned aircraft into the NAS is such a Herculean effort. Here in the United States, we arguably have the best air traffic management system in the entire world. During normal times, around 50,000 flights take off and land daily, with nearly 3 million airline passengers traveling across the more than 29 million square miles that make up the U.S. national airspace system. In that system, close to 15,000 air traffic controllers, 4,500 aviation safety inspectors, and 5,800 technicians operate and maintain services for our National Airspace System, or NAS. It has more than 19,000 airports and 600 air traffic control facilities. In all, There are 41,000 NASA operational facilities and over 71,000 pieces of equipment, ranging from radar systems to communication relay stations. With all of this infrastructure, integrating unmanned aircraft systems into the NAS will be demanding, to say the least. But this integration is of vital importance to our country because these new vehicles will be part of the next revolution in national security and defense, emergency management, science, and in commercial applications. For these reasons and more, NASA set out in 2009 to work on several main objectives for the project that included providing research findings that utilized simulation and flight tests, supporting the development and validation of detect and avoid and command and control technologies, and finally, the SIO demonstrations themselves. Two of the biggest challenges that needed solutions before the SIO demonstrations could take place was in the key areas of detect and avoid and command and control. For detect and avoid, one of the primary safety concerns with integrating these new systems is the inability of remote operators to see and avoid other aircraft. On all flights with pilots on board, the FAA requires the crew to be aware of all other surrounding aircraft, either visually or using onboard instrumentation. So in addition to instruments, the pilot physically looks out of the window to help safely avoid other aircraft. Because unmanned aircraft literally don't have a pilot on board, NASA and its partners worked on concepts and designs that allowed safe operation within the national airspace.
What detect and avoid is since the pilot for an unmanned aircraft is either remote off the aircraft or not there at all in the case of an autonomous aircraft, there is no human eyeball to go see other aircraft. So the technology needs to be developed to use other means, such as radars or cameras, to be able to detect where other aircraft are flying in the proximity of your aircraft, your unmanned aircraft, and then be able to somehow, like a pilot would, avoid those other aircraft. And the way that's done is through developing some mathematical algorithms to be able to direct the aircraft to a location that would be safe. And so that's the kind of research that NASA wanted to focus on, because that was the most critical aspect of how to safely integrate unmanned aircraft into the national airspace that industry writ large could not really understand.
The second hurdle was with command and control. Because unmanned aircraft are completely different from crewed aircraft, new techniques needed to be developed, including improving the avionics on board the UAS and on the ground. These aircraft must have reliable, safe, and secure data connections at all times while operating in the complex environment of controlled airspace.
Similarly, the command and control part of the UAS and the NAS project is based on the fact that most radio communications that are operated in the airspace now with pilots are voice communication. So it's a pilot talking to an air traffic controller or talking to other pilots, and they use voice to do that. Well, so the aviation spectrum that's been set aside for voice control doesn't work for an electronic control, because if you're going to control the aircraft through some sort of communication methodology, it's got to be done electronically, because you're sending a message to the aircraft to be able to turn or to be able to climb or descend, etc. And so, so the technology that NASA worked on was to develop a radio that could be used in that bandwidth, that spectrum bandwidth, to be able to send electronic messages to and from the vehicle, and thus be able to command the vehicle. So that's why the command and control work that's been done under the UAS and the NAS project is so important.
Over the years, researchers time and time again showed that they had developed the detect and avoid and command and control technology to the point where it could be reliably tested in real-world conditions. Although there were other flight demonstrations throughout this project, the last major hurdle of flying the SIO demonstrations is now at hand. NASA, in partnership with the FAA and industry partners, have begun the demonstrations of potential commercial applications using different sizes of unmanned aircraft systems for the SIO demonstrations. The goal of SIO is to work toward commercial UAS operations in the NAS. In order to accomplish this goal, NASA has partnered with 3 pioneering companies to conduct flight demonstrations in the NAS that emulate commercial missions and begin working toward Federal Aviation Administration or FAA type certification.
When NASA was selecting the partners for SIO, we went through a partnership process that included the evaluation of a number of candidate partners. And we were looking for some key aspects that these partners could bring to the table. And so the first was really great domain knowledge in unmanned aircraft and associated technologies. The second attribute was knowledge of certification and the knowledge that's really needed to kind of take these vehicles from the concept and early development stages through to becoming a commercial product. And then the third thing we were looking for are viable commercial missions that would be publicly beneficial. We really wanted to showcase how unmanned aircraft can play a role in the future of the world and have a positive impact. There's 3 different companies that are participating in the SIO activity: Bell, General Atomics, Aeronautical Systems, and AATI. Bell is bringing their AP-70 unmanned aircraft, which weighs approximately 300 pounds and is capable of vertical takeoff and landing and operations around urban areas. The primary mission that they're focused on is emergency medical supply transportation in an urban area. General Atomics is utilizing their Sky Guardian unmanned aircraft for multimodal long-endurance infrastructure inspection. That unmanned aircraft weighs approximately 12,000 pounds, so it's much bigger than the others that are participating in SIO, and is intended for an infrastructure inspection mission at altitudes above 10,000 feet. AATI is using their AI Ranger unmanned aircraft, which weighs approximately 180 pounds, for a pipeline inspection mission at lower altitudes between 1,000 and 5,000 feet. And then lastly, throughout this process, we've been collaborating with the FAA, who has provided extraordinary support and helped us to navigate the regulatory process that's in place for these demonstration activities.
The 3 partner companies are each using various sized and different types of unmanned aircraft configured for the SIO demonstrations.
Over the past several years, actually going back probably a couple decades, NASA has been working on UAS, first more in the technical side and now maybe more on the standard side. And I think the SIO activity was looking, or the objective was to address some of the gaps that still remain. And one of the ways that we were able to do that is by partnering with some companies to go after some of these things. The outcome of the demonstrations is to try to help the companies really get their arms around some of these barriers that still exist, work with the FAA to develop the processes, the solutions to be able to address some of these gaps, and then bring it to a place where the industry can learn off of those lessons. The aircraft that are participating in the SIO activity are really pretty unique, and they span quite a range. We've got airplanes that have propulsion systems that are all electric. We've got a turboprop. Another one is a piston powered. So from a propulsion side, they're pretty distinct. And then even if you look at the way that they just operate, you know, one takes off like a conventional airplane would take off from a commercial airport. Another one can basically launch off of almost anywhere and just land on some clearing. And then another one actually can take off also from anywhere, just vertically, and again landing vertically. So quite a range, even in altitudes, the way that they operate. Some of them were designed to operate at lower altitudes. Some of them were designed to be able to go pretty high, even maybe 40,000 feet.
Each company offers a unique perspective and engineering goal in performing the SIO tests.
So Bell's participation in NASA SIO is really about making sure we get the data that the regulators need to be able to understand not just the aircraft requirements, but the system environments for being able to get advanced aerial mobility actually into commercial space, integrated with the rest of aviation in the national airspace. Bell's actually been doing unmanned aerial vehicles for quite some time. From a commercial standpoint, APT is, a sizable vehicle, a little over 300 pounds, carries 70 pounds of payload. It's critical that we get this right so that we are safe and compliant in the airspace, and that's a part of what NASA SIO is about. They're a trusted data provider for the FAA and other regulators to be able to help us understand what really is required for the aircraft, for the airspace requirements, and then for the integration of those systems together. So NASA's involvement helps drive the technology to a high enough level that we have sufficient data for the FAA to make regulations. I would say the way it's being done right now is innovative. You see, NASA leaning forward with electric and hybrid propulsion, as well as, detect and avoid, and some of the things that we need for the airspace. You see the FAA leaning forward based on their small unmanned experience and knowing that we need to get out in front of this time to make sure that we do it right as we get to larger vehicles. And so that partnership and kind of active arrangement of let's discover together and work together towards what's both safe and economically viable as an overall community is really new.
On this particular mission, the APT-70 was armed from a ground control station, then was instructed to initiate a vertical takeoff. Per its design, it then rotated to fly on its wings, where it was nearly silent to the researchers below. It flew at an altitude of 500 feet above ground level, transitioned in and out of Class B airspace, all while staying in constant communication with the ground station through a redundant data link. On board was the prototype airborne detect and avoid system that provided the remote pilot with awareness of air traffic in the vicinity and recommended flight maneuvers. Initial results were promising, with more validation and testing to continue in the future. Another partner, General Atomics Aeronautical Systems Inc., or GA, flew their Sky Guardian aircraft. It had been used for unmanned missions for many years, totaling more than 6 million flight hours. For this NASA mission, a demo aircraft piloted remotely from California flew for 9 hours from its Gray Butte Flight Operations Facility near Palmdale, California, to Yuma, Arizona. Data was collected from the detect and avoid system to provide situational awareness of air traffic near the Sky Guardian. This system includes a traffic alert and collision avoidance system used in manned aircraft, which fly in civil airspace, and air-to-air radar to detect and track nearby aircraft that may not have active transponders. The particular aircraft in this test may provide services that include hundreds of miles of inspections of rail, power line, communication and canal infrastructure, agriculture monitoring and topological surveys, as well as wildfire and flood monitoring. According to GA CEO Lyndon Blue, quote, GA's work with NASA is opening the eyes of regulators to the safety and utility of unmanned aircraft systems and the performance of certain tasks for public and commercial good, end quote. Researchers believe these types of aircraft will also play an important role during crisis management events, such as wildfire containment. The onboard airborne sensors can see through thick smoke, enabling the craft to inform ground personnel about the location of fire lines so they can deploy resources more efficiently. The SIO demonstration also highlighted how the aircraft can be used for many other civilian and commercial missions as well. The third demonstration flight was a team from American Aerospace Technologies Incorporated, or AATI. Although AATI's craft was considerably smaller than the other test vehicles, its use case was invaluable. It can fly at medium altitudes and carry advanced sensors used to patrol our nation's more than 500,000 miles of midstream pipelines, providing a fundamentally new and unique capability that changes the way we manage health, safety, and the environment, respond to disasters, optimize operations, and leverage human capital.
So the mission itself serves multiple purposes. We're proving out the capability of beyond visual line of sight UAS in the national airspace. And the specific applicability for this mission is that we are looking for ways to make critical infrastructure inspection processes safer and more efficient. And so for this specific mission, the Air Ranger took off from our launch and recovery site, and we flew downrange along a oil pipeline which is buried underground, and we performed an inspection of the right-of-way of that pipeline. And we are proving out not only the applicability for critical infrastructure itself, but we're proving out the safety case for actually operating UAS in the NAS, not only utilizing the aircraft's technology for flight, but also utilizing different technologies for safety, such as detect and avoid systems, ADS-B, and flight radar notification systems for having situational awareness of not only what's in the airspace around us, but being able to tell others in the airspace that we're flying as well. In my opinion, to safely regulate and certify these types of aircraft to fly, you have to prove out three different things. You have to prove out that the aircraft itself is mission capable. You have to prove that the aircraft is dynamically capable to change for different conditions. And you also, most importantly, have to prove out the safety case. And so utilizing different types of technology, utilizing different processes and workflows, building the safety case around operating procedures, and integrating all of these different components aside from the actual flight itself, really build the roadmap and really set the stage for the rest of the industry to say, hey, look, this is what the infrastructure looks like. This is what the framework looks like to do this on an operational basis in the future.
Although the SIO demonstrations are now complete, NASA and industry will continue to move forward with exciting new technologies and hardware built on the foundation of successful data collection and testing from the SIO activity. The future of unmanned aircraft is bright. UAS will continue to advance scientific research, benefit environmental protection, assist with disaster mitigation, and move more people and goods to their desired destinations safely and efficiently for decades to come.
This was just the results of a project with a specific goal that we had within NASA Aeronautics. But it's certainly not the end. I mean, integrating UAS into the national airspace is an evolving thing. There are many more challenges. There are many more use cases that the industry is going to come up with. And so we're sensitive to that, and we're keeping an eye on that so that we can really align our research with those areas that are emerging, and hopefully so that we can enable those to really be to come into fruition for the benefit of the American public. And so as we stand up new projects, we'll leverage our experience with UAS and the NAS project, but we'll do it into new areas, whether it's autonomy or other areas of research that will really enable a lot of these use cases and bring about some pretty exciting new markets for the country.